Thank you. Good morning. Thank you in advance to the guys from the physics demo lab and also to all the other researchers from whom I've borrowed all the things that I put into this talk. The reason I came up with this title, The Secret Lives of Fluids, is because they asked me for a title several months ago, and I needed something sufficiently vague that I could talk about whatever I wanted. And I think this is sufficient. But what I generally had in mind was the fact that all around us in the atmosphere, the ocean, and elsewhere, fluids, which refers to liquids, gases, or plasmas, are at all times doing something extremely complicated. And usually we don't see any of it. Right? Occasionally, a cloud gets caught in an air current, or it's snowing, or you have some way of seeing what's going on. Right? A particularly spectacular example is the clouds on Jupiter. Right? They're contrasting colors. So in this time lapse from Voyager 1, right, we have this amazing view of the incredibly complicated motion. But the reality is that even this complexity, right, the smallest things being resolved here are enormous, right, hundreds or thousands of miles across. And if we were able to zoom in and in and in, we would find complexity on many, many, many scales, getting down to probably the human scale. Another example, these are measurements of sea surface temperature. Now, instead of clouds, it's the temperature that's being carried. Right, here's the east coast of the United States, and you can see the Gulf Stream, the hot fluid of the Gulf Stream, separating off. And it's giving you some hint of these motions, but again, only a hint. Here's a more local example. This is a toxic algae bloom in Lake Erie. And you can see the motion of the water being hinted at by the way the algae is being carried around. And Arbor would be off screen just to the left. Right, but it's really more than that. Every time you breathe out, every time you wave your hand through the air, right, there's complicated things happening. And these things taken together are very, very quantitatively hard to predict. And that's the challenge of fluid mechanics. So, convection. I'm going to talk in particular about convection. Right? Convection is a subset of fluid dynamics that's fluid motion driven by buoyancy. Right? This is essentially why the downstairs of your house is never much hotter than the upstairs. Because when air gets hot, it's less dense, it's pulled downward by gravity less strongly than colder fluid, right? And the hot air downstairs would flow upstairs, and the cold air upstairs would go downstairs. Right? Simple enough, but my colleague here, Charlie Dorian, is very fond of saying that convection is the most important unsolved problem in physics. This is an absurd claim, right? There are many very, very interesting unsolved problems, right? And many of them are quite esoteric. But in terms of what actually shapes the world around us and our everyday experiences, convection is, in fact, an extremely important process that's not very well understood. Here's a slice of the Earth. Right? On the upper layer is the atmosphere. Convection makes the wind blow. Convection creates thunderstorms. Convection creates hurricanes. These winds drive motion in the ocean, right? And there's also buoyancy-driven motions in the ocean due to differences in temperature or salt concentration. Below that, below the crust, is the mantle. Right? The mantle is not a fluid per se, but over very long time scales, it flows like one. And this is driven by heat, by differences in density. These mantle motions move the Earth's tectonic plates. Right? This is what shapes all the land around us. This is what builds mountains. Deeper still, the liquid outer core is made of iron. The outer core undergoes convection also. Iron is electrically conductive, so this moving fluid acts like a big electromagnet. This is what creates the Earth's magnetic field. Right? This is what creates the aurora borealis, protects us from the solar wind that would otherwise probably kill us, which is convenient. I think we can agree. Speaking of the solar wind, the outer third of the sun, right, heat is produced in the middle of the sun, then there's a radiative zone, then there's a convective zone, where this is the mode of transport. And we can see this. Right? Here's a video sped up of the surface of the sun. And you can see a bunch of granules. Each one is probably thousands of miles across. And what you'll notice is they're spreading outward. right? This is reflective of what's actually happening. As the plasma is coming up in the center of these granules, reaches the surface, spreads outward, falls down at the sides. Right? And similarly important processes are happening in other planets, other stars. So, convection is important. And probably the most familiar example is when you pour cream in your coffee. Cream is denser than coffee. It's not really the momentum that makes it sink to the bottom. It's the fact that it's heavier. So this is even more clear when you put cream in water. I'm assuming that you don't drink your water with cream. So let's see it right here. It happens quickly. And so it's on those two side screens. But if you can see here. It's quite a mesmerizing thing. And in fact, here the guys from the demo lab made a slower motion video. So the thing to notice is that even on this incredibly small scale, there's such a complexity of structure on this shape. So it's easy to describe, say, convection is everywhere, it's really cool, and it's complicated. But when you look at things physically and you're actually trying to make quantitative predictions, the fact that it looks like this means that's going to be very difficult. Right? If you have a problem, you do in school, you have a certain equation, you solve it, the answer is the shape is sine of x times sine of y. That's never going to happen here. Right? This is not sine of x times sine of y. This has incredibly complicated variation in space and time. If you're thinking that this looks something like the explosion of an atomic bomb, you're right. Right? Here it was cold fluid sinking and creating a plume. Here it's hot air rising and creating a plume. And the visualization is due to condensation of water vapor. Okay, a brief aside, a brief lesson in geophysical fluid dynamics. Rotation matters. Right? I will say nothing more about this except that on large scales, we live in a rotating reference frame, right? The Earth is rotating, and this makes a difference. It doesn't make a difference on the human scale. Thank you. So, I'm going to repeat this experiment in rotating water. Not the same. Essentially, just the way a spinning top is held from falling over by gyroscopic forces, this plume is prevented from spreading out by Coriolis forces. And I will have nothing more to say about this because it's just too much material to cover at once. But I would point you to the website at this URL of my friend John Arnaud at UCLA, who has a lot of cool demos like this, including this one, which I stole from him. So if you want to learn about rotation, you can go there. I'm going to focus on something simpler. This is something called Rayleigh-Bénard convection. And it's named for the minor British aristocrat Lord Rayleigh and the French physicist Bénard. Now, all these configurations I've talked about are very complicated. I now want to come up with the simplest conceivable configuration in which convection will happen, and then see if we can make quantitative predictions about it. And that looks like this. We've got a cold plate on top. We've got a hot plate on the bottom. Right? We maintain these temperatures. If we've got air or water in the middle, right, the stuff near the bottom is going to be heating up, getting less dense. The stuff near the top is going to be cooling down, getting more dense. It's going to want to turn over. This is it, right? And so hopefully we can answer quantitative questions about this simplest possible configuration. If we can't do that, right, we don't have a very good hope of making predictions about the atmosphere. So the first way we can study this is with laboratory experiments. Right, here's a cylinder of water. There's some reflective particles floating in it. And the bottom's hot, the top's cold, and we're shining a sheet of laser light through it. So we're getting a two-dimensional slice. So this is real time. So not too much is happening, right? It's happening slowly. But we're certainly getting a glimpse. And we can measure from a physical experiment bulk properties. We can measure the amount of heat that's being transported through. We can try to get the kinetic energy. But we can't look in extreme detail, right? You can't say what's the temperature at every point at every moment in time. That's just too difficult. So to do that kind of thing, we want a theoretical treatment. Right? Forget about temperature for a minute. Let's assume that our fluid is of constant density. Fluids are usually governed well by a set of equations called the Navier-Stokes equations, named for the French physicist and engineer Navier and the Irish-born mathematical physicist Stokes. The Navier-Stokes equations tell us, all right, we've got a velocity, u. That's really a vector. It's got velocity in all three directions. And we need to know how it varies everywhere in space, x, y, and z, and how it varies as we move forward in time. I called that t. Right? We've also got pressure. That's all we need. The equations look like this. Now, I'm assuming that you're all brushed up on your partial differential equations. But just for redundancy, the top line is essentially conservation of mass. Right? If you have a pipe and water is flowing in at 10 grams a second, it's flowing out at 10 grams a second. The bottom line is actually three equations written in a compact form. It's just conservation of momentum, right? Conservation of momentum in all three directions. Right? It's that simple. But let's step back for a minute and say, are they good equations? Right? These are the central equations of fluid mechanics, which is a classical field of physics. And every time physicists write down what they think is sort of the central equations of their field, mathematicians come along later and they do kind of the due diligence and make sure that these equations have the properties that you want equations to have. In particular, you ask, does the future exist and is it deterministic? Right? Mathematically, this means if you tell it how you're starting, these are exactly the velocities, this is exactly the pressure, and you solve the equations forward in time, which should predict all future states, do you reach a time beyond which that breaks down and the solutions cease to exist? Right? This is the sense in which the future would fail to exist. Furthermore, assuming the answer is yes, you want the future to be unique. Right? Our experience with the world is that it's deterministic. We like our physical laws to be deterministic. You don't want to have a unique starting position potentially leading to 4 different futures. Right? So this is the mathematical due diligence. The answer in 2 spatial dimensions is yes, everything's good, no problem. This is great. You might have noticed that we live in 3 spatial dimensions, string theory notwithstanding. This remains the million-dollar question, quite literally. It has not been answered one way or the other, and the Clay Mathematics Institute is offering $1 million for its resolution one way or the other. So feel free to take a crack at it. But I can assure you that engineers are not losing any sleep over this problem. Right? They don't care. The equations work pretty well. They solve them. They build cars, airplanes, and everything. So let's just use them. And let's add temperature, because now we need temperature creating differences in buoyancy. So along comes Boussinesq, French physicist, and he comes up with these equations that are in a sense an approximation, but they're basically the simplest way we can capture convection without further complication. Right? So we've got Navier-Stokes equations telling us how velocity and pressure change. Now we need something for temperature, capital T. And all you do is add a third line, a temperature equation. So we've got these equations telling us how U, P, and T evolve. And there's only 2 other symbols written in here, PR and RA. So let me define those. The PR is the Prandtl number, named for German engineer Ludwig Prandtl. RA is the Rayleigh number, named for Lord Rayleigh. So this situation I've described, a box of fluid, hot on the bottom, cold on the top, it has a lot of physical parameters in it. right? It has a certain viscosity, temperature difference between the boundaries, how big it is, how strong gravity is. But it turns out that if you write the equations in a certain way, you can make it so that all these parameters are grouped together, right? And it doesn't matter what their individual values are. It only matters what their collected values are. So the Prandtl number just depends on how thick the fluid is, its viscosity, and how well it conducts heat. You can think of it as an intrinsic property of any given fluid that doesn't much change. In air, it's about 0.7. In water, it's about 7. The Rayleigh number, on the other hand, depends not only on the fluid, but on the configuration. In particular, it's proportional to the temperature difference between the boundaries, right? So if you make the bottom really hot and the top really cold, the Rayleigh number is bigger. If the bottom and top are the same temperature, the Rayleigh number is 0. So in a sense, the Rayleigh number is our tunable parameter that's saying how hard are we driving the flow, how vigorous is the convection going to be. All right, so back to the simplest possible problem we can study. Now we have equations. Let's try to solve them and see what we can predict. The simplest question you could possibly ask is, when does convection happen? Is it sufficient that the bottom be hotter than the top? Does it need to be hotter than the top by some certain threshold? The answer comes from Rayleigh, which is how he got his name on this problem. And he said that the Rayleigh number, which of course he did not call it, that would be a little ostentatious. He said that the Rayleigh number has to be greater than 24 times pi to the fourth, or sorry, 27 times pi to the fourth divided by 4. Right? It's amazing how pi pops up everywhere. And we now know that the converse is true as well. If the Rayleigh number is smaller than that number, convection will not occur. This is already a non-trivial statement, right? Because that's saying it's not sufficient that the bottom be hotter than the top, because you have to overcome viscosity, right? The bottom has to be hotter than the top by a certain threshold that's calculated from all the collected parameters of the problem into this Rayleigh number. All right, so that was really a breakthrough of analysis. You know, it's just pencil and paper analysis. But actually, okay, for convenience, he assumed that the top and the bottom were slippery. But in reality, if you put fluid in a box, it sticks to the walls. So, okay, no problem. 12 years later, somebody came along and said, okay, the walls are sticky. It's about 1708. Okay. So we know that when the Rayleigh number is less than 1708, nothing happens. So the temperature distribution is going to look like this. Cold near the top, blue. Medium in the middle, green. Hot near the bottom, red. Okay, when the Rayleigh number is greater than 1708, stuff happens. That's when it gets a lot harder, right? What exactly happens? What are the quantitative features of the flow? What does it look like? Well, can we continue to proceed by hand? Can we just work with a pencil and paper? You can, right? And it's a lot more work. People have written over 100 papers on what happens. But you can only do it when the Rayleigh number is slightly larger than 1708. This is not that useful scientifically, because in the atmosphere, it might be larger than 1 trillion. In the sun, it might be 10 to the 22. So we really can't work by hand. Think about this plume of creamer, right? There's no way we can write down an equation that's going to tell us how that shape evolves. So we have to resort to numerical methods. This is the simplest case in which I could say what a numerical method is. Suppose we have to solve this equation for y, x minus 2y equals 0. Well, you can surely all do this. You would just say, okay, yeah, do some algebra, y equals x over 2. This is what's called the analytical solution. It's done symbolically. You get an answer for y that's valid for any x. We can't do this on hard problems, right? We can only do this on textbook examples. So suppose this equation was too difficult for me. I said, yeah, I don't know. I can't figure it out. But you would say, all right, well, what about for a particular x? Can you do it? So you would say, okay, x equals 2. Then I say, all right, 2 minus 2y equals 0. Okay, yeah, now I can do it. Y equals 1. Well, that's how we solve the Boussinesq equations, but it's much harder. So what we do is we chop space up into a grid, right? We take something that was modeled as varying continuously, and we model it discretely. And instead of asking for the velocity and the pressure and the temperature everywhere, we just ask for it at the grid points. And By doing this, we're able to replace the original equations, which are essentially a calculus problem, with an algebra problem. Right? You have an algebraic relation between how the pressure and temperature at a certain grid point are going to change, affected only by its neighbors. Right? So this is very convenient in a way, and time as well is discrete. So instead of moving continuously in time, you take little time steps. So you've taken a very small calculus problem and replaced it with an enormous algebra problem, right? Because you have these relations at every single one of these grid points. And in fact, we still can't solve this algebra problem symbolically. As on the previous slide you could. Here, no way. But you can solve it numerically. I can say, if these are exactly my starting conditions, this grid point temperature is 1, this grid point temperature is 5, right? I lay out all the numbers. You have now a giant arithmetic problem. All right, so I went from calculus to algebra to a huge amount of arithmetic. The pioneer in this kind of, one of the pioneers in this kind of idea was Lewis Fry Richardson, a British meteorologist. He had a similar idea. This was around 1910, 1920. He wanted to predict the weather, not just by looking at weather maps. He wanted to actually do calculations. So here's a map of Europe. This is from his book. You chop it up into a grid. Each square is a weather station. That gives you your initial data. You take your equations that you want to solve, you approximate them with algebraic equations, you put in your initial numbers, it becomes an arithmetic problem. Unfortunately, it involves a huge amount of arithmetic, right? If you have a lot of grid points, there's just so much arithmetic to do at every step. So when I say huge amount of arithmetic, what naturally comes to mind? Yes, you're all correct. British schoolboys. This was 1915, right? There were no digital computers. In fact, they referred to the people who did the computations as computers. So the idea was something like this. He would set up a bunch of desks in a room. Each square would be a desk with an underpaid British schoolboy sitting at it. He would do his calculations for his grid point, hand the relevant answers to his neighbors, and they would proceed like this at each time step. It was a visionary idea, and it sort of worked, but it didn't quite take off yet because he needed digital computers. So, fortunately now, we do not have to violate child labor laws because I can do this on my laptop in 5 minutes, and it doesn't make mistakes. So let's try it. We've got this numerical method implemented. I'm going to make the Rayleigh number 1,000. Remember that magic number, 1708? This is below that. So Lord Rayleigh's analysis says nothing should happen. Well, I kicked up the temperature. I messed it up to try to make something happen. And I'm going to start solving the equations. And indeed, very boring, right? Nothing happens. But now let's go above 1708. Let's go to 2500. Now I kicked up the temperature, right? Try to make something happen. Solve the equations. Well, it's not dramatic, but something happened, right? It will stay like this forever. We're only looking at temperature here, but you might be able to infer what the velocity is doing, right? Everywhere the red fluid at the bottom boundary is thicker, that's where it's being pulled upwards. Everywhere the blue is thicker, that's where it's being pulled downwards. And in fact, it's uniform in depth. So it's settled on a two-dimensional pattern, even though I didn't impose true dimensionality. Sometimes that happens, usually not. Right, and this not being a laboratory experiment, I can look in any level of detail. So let's put, right, we've settled on this pattern. Let's put 8 imaginary particles in the flow. And let's just see how they would be carried. That's it. They'll just go around like that forever. So the flow has settled on an unchanging, simple pattern, and we can study its quantitative properties, how much heat it moves, and so forth. Right? But it's not quite so simple. Here's a different pattern. This pattern is 3-dimensional, not 2-dimensional. I arrived at this by calculating with the exact same Rayleigh number, the exact same Prandtl number, and the exact same configuration. The only thing I changed was the initial conditions. Right? So the pattern that you settle on is not unique. In fact, there can be an infinite number of possibilities. Right? So this is problematic. And in fact, this is what Baynard originally did before Rayleigh. This is how the problem really became established as a favorite model problem. Baynard took these very thin layers of fluid, heated them from below until they started to move. Notice that there was a critical amount of heating that was needed, right? A little bit doesn't do it. You pass some threshold, and they form a pattern. This is not his photograph, but he made photographs like this. So seen from above, you see something, all these polygons, mostly hexagons. And it's like the fluid is coming up in the middle, and it's falling down at the edges, or vice versa. So in a big domain, right, it can settle onto anything. In fact, the fluid that he used for most of these is something called spermaceti, which is a wax that comes from a giant organ in the head of a sperm whale. So if you have access to a dead sperm whale, you can attempt to repeat this. All right. Other things can happen. This is a video from the website of Stephen Morris. He has a lot of cool videos, and I suggest you check him out as well. He's at the University of Toronto. We're looking from above again, a thin layer of fluid, heated below, cooled above. What appears to us as light are regions where the fluid is falling downward. And what appears as dark are regions where the fluid is coming upwards, towards our eye. Amazing, I think. Right. So you have this incredible collection of patterns. All of it is very cool from the standpoint of pattern formation. But again, let's try to get back to quantitative description of really complicated flows, the atmosphere, and things like that. All right, so now let's crank the Rayleigh number up. Now it's 100 million. Here's a video from my collaborator in the Netherlands, Erwin van der Poel. So he starts with some fluid, and he's not showing the stuff that's of average temperature. So initially, you see nothing. He's only showing the hot stuff in red and the cold stuff in blue. And he turns on the boundary temperatures. It starts going, and it never stops. This is starting to look more like reality, right? This is what that plume of cream looked like. Another video at a Rayleigh number of 1 billion from Jörg Schumacher in Germany. Now we're going to look at a surface of constant temperature. Right? So there's very fine features, and you can get an idea of the way the fluid is moving from the way it carries the temperature. Okay. Let me stop now and ask a bunch of questions. Right? Not to you, to rhetorical questions, but you can answer them. I hope I've shown you enough cool videos to get you interested, and now I'm going to try to explain where this field is, what works, what doesn't, and why it's difficult. First of all, how many grid points do we need? Right? Well, basically, you have to resolve all the features of the flow. Right? The grid should be finer than any feature. So in those first videos where it was just one big pattern, you don't need a lot. Right? Here, in those later videos I showed you, you do really need a lot of grid points. In those last two videos, 10 million, 50 million, 100 million, something like that. Right? So schoolboys would not be sufficient. Instead, we use supercomputers. But you'd have to break the problem up. It can't fit on any one processor or in memory. So you take 100, or rather 1 million grid points, 10 million grid points, give them to one processor, 1 million go on another processor. Just like the schoolboys passing the notes from desk to desk, the processors talk to each other as needed, and they solve these massive equations. We observe, although we cannot prove mathematically, that the larger the Rayleigh number is, the more points we need. Right? And there is a certain scale below which we don't need to resolve. If you make the mesh finer and finer, eventually the answer stops changing, and then you're pretty confident that you got the right answer. The reason that nothing happens below a certain scale is molecular diffusion. Right? Viscosity, which tends to smooth out differences in momentum, thermal diffusion, which smooths out differences in temperature. These things are not very strong processes, but they become more and more effective the smaller the scales. So all these other momentum-driven processes are dominating at large scales, but eventually at small scales, not that much is happening. Okay, so we've got a method, we've got equations, and we know how to solve it approximately on a giant grid with a supercomputer. Would this work well for the atmosphere, the outer core of the Earth, the sun? Right? These are very complicated systems, and we want to predict quantitative features. For example, with the core, we might want to know how strong is the magnetic field it's producing. When is it going to reverse? Right? Reversals could be bad for us because when the magnetic field goes away, we're not protected from the solar wind. The atmosphere affects not only predicting the weather, but the climate, right? We want to know the long-term climate. The answer is yes. This would work great, several technical caveats aside, such as problems with the finite precision of arithmetic on computers. But even if we could do this perfectly, we still wouldn't know next month's weather, right? Our inability to predict the weather is an inherent limitation on the system. This is what you've probably heard called the butterfly effect. A very, very small difference in today's weather will create a massive difference that makes next month's weather unpredictable. But, okay, forget that. We would get average quantities, right? We would get things related to the climate, which I think we can agree are very important. Great, this would work. Can we do this? Nope. No chance. No chance, right? Remember I said in the beginning, in the atmosphere, for example, right, you've got hurricanes, you've got all this global scale circulation. You've got relevant motion on every single scale down to, a centimeter. And those centimeter scales have an interaction, right? They affect the slightly larger scales, which affect the slightly larger scales, which affect the biggest scales. And nothing that can really be ignored. Even if we extrapolated our present computing power for 50 or even 100 years, right, it doesn't seem likely that we're going to have a grid covering the entire globe at 2-inch spacing, and we're going to solve equations on it. I mean, we couldn't even do this room, not even close. Right? So, okay, we can't do it. The grids we can afford are much, much too coarse. However, the problem is that we can't just chop off small scales. Right? You might say, all right, well, surely the small stuff is less important than the big stuff, so just make the grid as fine as you can make it, solve the equations, and that's your best answer. That will be catastrophic. Right? Neglecting the physics completely below the scale you're resolving, if you're not going small enough, you just get garbage. So the solution is that you need something called a subgrid model. A subgrid model means you have to somehow model the effects of the smaller scales that you're not resolving on the larger scales, on the largest or the smallest scale that you can actually afford to resolve in your computation. All right. I'm sorry I don't have any videos in this section, but this naturally leads us to the question, do subgrid models work, right? We use them all the time. Every time you design the flow past a car, past an airplane, predict the weather, do anything, right? We can only afford to really completely resolve things that are so small and trivial. Every industrial application contains subgrid models. Do they work? Sometimes. Sometimes they work very well, and sometimes they fail completely catastrophically. You shouldn't worry about this in terms of flying in airplanes or trusting the weather prediction, because subgrid models work very well when we kind of know the answer. Right? It's because they really can't give us any new enlightenment. If we sort of know the answer, we build it in and we get it out. Right? You have a lot of data on how the atmosphere behaves under so-and-so conditions. You build that into your model. We know how air moving at a certain speed around an airplane wing, right? We kind of know all the numbers from many similar cases. You build that into the model. It doesn't work for extrapolation. Right? So if we want to know what's happening on the sun, if we want to know, well, other planets. Rayleigh numbers 10 to the 22, 10 to the 16, these absolutely cannot be done in a laboratory. We have no data. We can't do the math. We just have no idea what happens out there. So I would say this means we need to go back and try to understand better the basic processes. Rayleigh-Benard convection, for example. Let's look in detail at Rayleigh-Benard convection and try to make quantitative predictions. Right? I showed you some patterns, but what do we really want to know from these very, very complicated cases? We want to know average quantities. And in this little cottage industry, everybody's favorite average quantity is the Nusselt number, named for this German engineer, Nusselt. The Nusselt number is the heat flux coming through the fluid with motion, right, in what's actually happening, divided by what the heat flux would be with no motion. Right? If you were magically able to keep the air still as if it were a hunk of metal, right? So it's an amplification factor. How much is the heat moving because of the convection relative to if there were no convection? And I can tell you that this is always at least 1. The motion that's driven by the differences in buoyancy will only enhance heat transport. In fact, it does so significantly. Molecular diffusion by itself is incredibly slow over large scales. If you turned your heat on in the fall and there were no convection, right, the heat were just diffusing through your house, it would be spring before your house was warm, quite literally. And you'd probably have frozen to death in the meantime. So you should be thankful for convection. Okay, so we've got this heat transport augmentation. It's just one single number we want to get. So we say what the, damn it. We say what we want. Nusselt is a function of Rayleigh and Prandtl, right? So I tell you the Rayleigh number. Okay, it's 20 billion. Prandtl number is 7. Now you tell me what the Nusselt number is going to be with quantitative precision. This is a very hard problem. Also, this is not really a function. You may remember from school, a function is something where you put in the inputs and you get a unique output. That's not the case here, right? Because I haven't told you the initial conditions. And in fact, you can't know them. You can't know them with the necessary precision, right? That original example where you can fall onto one pattern or another, or the hexagons or the spirals, each one of these patterns that you fall onto will have slightly different quantitative properties. So, all right, it's not a function. Maybe it's a multi-valued function. I want to know every possible value, or I want to know the range of values. What's the biggest it could ever be? What's the smallest? Right? So we can still pose questions that are precise. And I thought at this point you might be getting bored of all the text, so. Right. Let's remind ourselves, this is what we're talking about. I don't care about all that detail. I don't want all that detail. I want one number, right? Here are the conditions, how much heat is being moved. It doesn't seem like we should have to compute, billions and billions of arithmetic operations to get one number. Okay, well, what have we figured out about this? We want to try to do analysis first. Let's just take the equations, right, the Boussinesq equations. Let's do mathematical proofs. Well, not too much. We can prove that the Nusselt number is no smaller than 1, meaning that convection only increases heat transport. Right? A physicist would have said, that's obvious, why are you wasting our time? We can prove also that the Nusselt number cannot grow with the Rayleigh number faster than 0.034 times the square root of the Rayleigh number. That's less obvious, but a physicist would still say, that's obvious, why are you wasting our time? But myself being an applied mathematician, I like when we can prove things. So what does this say? Well, suppose the Rayleigh number were 1,000,000, as it might be when you're boiling water on the stove. This says that the amplification of heat transport by the motion of the fluid is somewhere between 1 and 34. I think you'll agree that's not very precise, right? That would be a severe problem. So this is not good enough, right? We're trying to do better mathematical analysis, but we just can't right now. So we have to resort to experiments and simulations, like that movie that I showed you in the beginning. right, of the experiment in the water. We do things like that. People have been doing them for 100 years, very precisely, a huge amount of data, a huge amount of work. They just turn it on and they measure how much heat is coming through it. So we've got a lot of data. What to do with it is another matter. And then simulations, as I talked about. We create meshes, we do computations, right? We get all the numbers out, and we can get more numbers. It's a simulation, so we can look at any statistic we want. We can look at any grid point we want. Right, so we have a glut of data in the accessible range. But we can't get too far, right? We can't get to the sun. We can't get to the core of the Earth. We can't reach these conditions. So, well, what do? Extrapolation is not reliable. So people come up with approximate theories. People come up with theories like they make some kind of compelling sort of physical argument, right? This should be of the order of magnitude of this, and you can come up with approximations. And these give you educated guesses. These are much better than blind guesses, but they're not perfect. Right? You can come up with a very compelling argument that when the convection gets really, really strong, like in the sun or the Earth's core, that the Nusselt number should scale with the Rayleigh number like the square root of the Rayleigh number. Okay, that's good. You can also make a very compelling argument that it should scale like the cube root of the Rayleigh number. That's problematic, right? We don't know which the answer is. So, is there a shortcut? Right, I said that the mathematical well-posedness of the Navier-Stokes equations is the $1,000,000 question. This is more like the $100 billion question or the $1 trillion question, right? The industrial applications of a shortcut to this kind of thing would be massive, right? Every airplane we design, every oil pipeline, everything involving heat transport, right? I just want to know one number, right? The temperature difference is this. I'm using water. How much heat is transported? Doesn't it seem kind of absurd that we have to make these massive grids and do these billions and billions and billions of calculations? There should be a better way. Unfortunately, this is essentially what's called the problem of turbulence. Turbulence in this context is not a bumpy airplane ride. Right? Turbulence is complexity of fluid motion existing across all scales. And the problem of turbulence is, can we get a shortcut without resolving all these small scales, without all these seemingly not that relevant details? Well, this problem appears to be very, very hard. It's sometimes said that this is the hardest unsolved problem in classical physics. And my personal opinion is that we're not close to a solution. Although that's the thing about major breakthroughs, you don't always see them coming. I'm not close to a solution. All I can really say is that we're working on it. And I have a few other videos that I can show more related in detail to my own research. I realize that I've finished early, but that's the end of the main portion of my talk. So thank you very much for your attention.